So we stopped that there are certain problems with the regular Gauss elimination algorithm, that sometimes we divide by 0, sometimes we have a very high error that propagates from one step to another because of the truncation, because of the round-off error. And we said the solution to this problem is partial pivoting. So we will have some examples to demonstrate how we can apply the partial pivoting. Plus, we will talk about some certain examples about circuit, where circuit fits into the linear algebra problem. So we have this system. It said that we need to solve it using Gaussian elimination with partial pivoting. Okay, and we will use 5 significant digits. This is exactly the same example I showed to you before. If you recall this example, we said that this is when we talked about the problems with Gauss elimination. This is the same example. When we used 5 significant digits, the answer was 0.6251, 0.5, and 0.99995, while the actual answer is 111. So we'll see now if we apply this, the partial pivoting, how this can help us to minimize or get rid of this problem. Okay? So how to apply partial pivoting? So let's start. So we'll start with the first column. Now, in the first column, we will we'll check the column. Now, 20 minus 3 and 5. Now, 20 is the largest number, so I don't need to do any swapping. So I will just continue as the system is. So no need to do any row switching. Okay. So let's move on. And let's see how we'll do this. Okay, so this is my system of equations that I will have right now. Okay, so I will have 20, 15, and 10 minus 3 minus 2.42. Sorry. We just remove this eraser. So it is minus 2.249 and 7. Then I will have 5, 1, and 3. And then I will have 45. 1.751 and 9. Okay, so this is my system. Now the first thing I wanna make these equal to zeros. So how I will do this? It will be row 2. I will not do the math. You can do that yourself. So it is here for row 2. So it will be row 2 minus 3 over 20 times row 1. So I will multiply row 1 with minus 3 times 20, and then I will subtract this from row 2. So the first, as we know, the first line will be the same, 45, and then I will have 0.001, 8.5, and 8.501. And I will have here 0 minus 2.75. Okay, for row 3 now, it will be like row 3 minus 5 over 20 times row 1. Okay, so you as we said, we divide this by this, and then we subtract the third row times minus the constant that we found from this division, which will multiply it by the whole row. Okay, and this is 0.5 minus 2.25. So now we are done with the first column. Now we'll go for the second column, and we will start from the KK element, means the diagonal element, and we'll compare it with the rest. So we have only two elements, and obviously that minus 2.75 is larger than 0.001 as absolute value. So I need to interchange these two lines, 20, 15, and 10, 45. This is nothing happened there. So I will swap this. So this becomes 0 minus 2.75. And this will becomes here it is 0.5, sorry, 0.5. I will address your question after I finish the example. I will check all your questions. 0.001, 8.5, and 8.501. Now everything is clear. Okay, I can do it now. So I need to deal with these two rows only. I want to make this equal to 0. And how to make this equal to 0? You would just need to subtract row 3 minus 0.001 divided by minus 2.75 times row 2. And if you do this, you will find that you will get the following matrix. I don't need to show it to you right directly now. This is what you will get after that. So now we can do back substitution starting from here. So 8.5, we use five significant digits, 1, 2, 3, 4, 5, x3 equal to 8.5001. So from this, x3 equal to 1. And then we go and back substitution, so minus 2.75 x2 plus 0.5 x3 equal to minus 2.25. This is equal to 1, so minus 2.75 x2 is equal to minus 2.25 minus 0.5 times 1, which make x2 also equal to 1, and also you will find that x1 is also equal to 1. Okay, and this is the exact answer. So by doing the partial pivoting, we were able to find the answer, correct answer to this problem. And I used the same thing, 5 significant digits. Let me see your question here. I think we add 5 over 20 row 1 to row 2. No, we subtract. We always subtract them. We don't add rows. So we multiply with the sign of the row and then we subtract them. Okay. Let's move on. So here this is some interesting examples I found that it shows some special cases when you deal with linear systems, and when you develop your algorithm you might encounter these. So you need to understand what is the meaning of this. Okay, so this is a 4x4 system. Okay, so we want to solve for this. So this is the first, we have x1, x2 until x4 as our unknowns. So we need to solve this system. So, okay, again, straightforward. Again, it's a good also exercise to do this step by step so that we will get the hang of it. So I'm just writing down the system, minus 2, 3, minus 5, 3, and 8, 6, 3, and 9. Okay, so now I want to get rid of all these zeros. So it's very obvious it will be row 2 minus 1/2 row 1, row 3 minus 1/2 row 1, and row 4 minus 1/2 row. So everything is, because these are all 1, so I need to have multiply by 1/2 and then subtract with row 1 for all of them. Okay, so this stays as it is, minus 6, 4 minus 2, and this is 8. Then if I do this, row 2 minus half row 1. Okay, so this will become equal to 0, 0, 2, 4, 2. Then same thing, row 3 minus 1 half row 1. So this becomes 0, 2, 0, minus 4, minus 1. And finally, row 4 minus 1 half row 1. This is becomes 0, minus 1, 1, 4, 5. Okay. So now the partial pivoting is always there. So we have to check it. Now, if you look here, we compare the diagonal element with everything below. So it's obvious that this is higher, so I need to interchange these two rows. So I will have 2 minus 6, 4 minus 2, 8. Then I will have 0, 2, 0, minus 4, minus 1, 0, 0, 2, 4, and 2, and 0, minus 1, 1, 4, and 5. Okay. Now, what I want to do, I already get rid of this. So now this becomes 0, so I don't need to touch. So I need just to do row 4. Okay. So it will be row 4 minus 1 half row 2. Okay. So it will be row 4 minus 1 half times row 2 to get rid of this one and make everything is 0. So I will have 2 minus 6, 4 minus, I will just copy everything, 8, 0, 2, 0, minus 4, minus 1, and then 0, 0, 2, 4, 2, and then this becomes 0, 0, 1, 2, 4.5. Now, this is the last one left, so I will have here, I will have only row 4 minus 1 half row 3. Now, this is the interesting part here in this question. This is what I will get. If I do this, I will have 2 minus 6, 4 minus 2, 8, and then 0, 2, 0, minus 4, minus 1, and then 0, 0, 2, 4, 2, and then 0, 0, 0, 0, 3 and a half. So what does this mean? When I say 0, so this becomes 0 equal to 3 and a half, which doesn't make any sense. So if you encounter something like this, it means that there is no solution to this system. Okay, what does it mean that a system, physically, what does it mean that the system has no solutions? If we look to this one, this is just two variables to make things easier to visualize. If you have something like this, the system has no solution. It means if you look here, these are two parallel lines. This is the x1 and x2. So we have the two. This is the first equation. This is the second equation. If we draw them in a two-dimensional space, you will see that these two lines are parallel. They will never intersect. So it means that there is no solution because there is no intersection. So it means that there is no any solution to this problem. Okay, so this is one of the practical things, and later on we will see how we can implement this in into real systems. Okay. Now let's see this one. It's a different system, and we will use the Gaussian elimination with partial pivoting. So I will not do this. I will just show you the answers for that. You have the answers. You can practice this. But I'd like to highlight something also very interesting here. So this is the solution. You can just go and check this one. I just changed a little bit from the previous. Now, what we have here, we will have at the end 0 equal to 0. So this can be taken out. So now I will have 3 equations with 4 unknowns. If I have 3 equations, but I have 4 unknowns, it means what? It means I have an infinite number of solutions. You have many solutions, an infinite number of solutions. What does this mean? Again, physically, if you have an infinite number of solutions, it means that the two lines, if you're trying to solve a two variables, two equations, they are on top of each other. So there is an infinite number of points that they are touching each other. Then this is what we say, we have an infinite number of solutions. And when this will happen, when you, for example, produce two equations, they are actually the same equation, but you just multiply by certain factors. So it's basically the same equation. There is no difference between these two equations. Now let's have, this is what is really I like to introduce to you, which is including some circuit questions. Okay, so where we see these problems, an infinite number of solutions or no solution to a circuit problem. So if we have something, this would help us to understand some of the basics that we know, maybe for a fact, we don't understand why, in circuit one. So if I have this simple circuit and I want to find my currents, I1, I2, and I3. So imagine I take KVL in this loop. So it is basically KVL to loop number 1. Okay, so it is 2I1 plus 3I2 equal to 10. So this is my first equation. Then I will take KVL to the second loop. So it is 3 KVL to loop number 2. So we have here 2I3 plus 3I2 equal to 5, equation number 2. Now, let me assume that I will take a KVL for the outer loop. Okay, I will take a KVL for the outer loop. My third equation. I need three equations because I have three unknowns. So okay, this will becomes equal to 2I1 minus 2I3 plus 5 minus 10 minus 10 equal to 0. Okay, let's take KVL of the outer loop, and then this will be my system of equations becomes 2I1 minus 2I3 equal to 5, equation number 2. So I have three equations. So I will put them in matrix form. So this is 2, 2, 3, 0, because there is no component of I3 in the first equation, and this is equal to 10. Then I will have in the second equation, there is no one, so this is 0, and then we have 3, and then we'll have 2, and this is 5. And then finally, I will have 0, the last one, we'll have, 2, and 0, minus 2, and 3. So I have everything here I need. So, okay, I look to the first one. Okay, they are equal, that's okay. I don't need to do anything. So I will just subtract from here. I will subtract row 3 minus row 1. So I will have this 3, 2, 3, 0, and 10. Nothing happened in the first row. Then I will have 0, 3, 2, 5. Equation 3 equal to 5. Yeah, it is equal to 5. Yes, you're right. This is 5. And this has to be 5 as well. Thank you very much. This is 5. Thank you. And then this becomes 0, minus 3, minus 2, and minus 5. Then I will add row 3 plus row 2. If I do this, I will get 2, 3, 0, 10. Second row as it is, 3, 2, 5. If I add these two rows, it becomes 0, 0, 0, and 0. And this is the case, we will have an infinite number of solutions. Why is that? Because actually the equation number 3 is nothing but it's a combination of equation 1 and 2. If you subtract equation 1 from 2, you will get equation number 3. Why? Because loop number 3 is nothing but the combination of loop number 1 and loop number 2. We have to have 3 independent equations. And this is why maybe you recall that in circuit, the professor might have told you that whenever you want to apply KCL and KVL, you cannot solve most of the problems using either KVL or either KCL. You have to use both. And this is one of the drawbacks of the KCL, KVL as compared to the nodal or the mesh. In the nodal and the mesh, it's very systematic. You will get the same number of equations, the same number of unknowns. Anyone can solve this in any place in the universe, and he or she will get exactly the same equations. But if you deal here, you might have different equations. And you have to combine KCL and KVL to get 3 independent equations. So this is a practical example where you can see that you will have an infinite number of solutions. This is another example that shows you something else in circuit that is also stems from linear algebra. You might have heard the term, but you don't maybe understand what does it really mean in physical system. So let's solve this one. So I have here this circuit. Now this is 1/2 V1, 1/2 V1. This is 1/3 V2. V2 is the variable that I want to find. Okay, so this doesn't matter what is this element is, and I have these 2 voltage sources. Okay, so I will take KVL to loop number 1. So I will have here V1 divided by 2 plus V1 divided by 2 plus 1/3 V2 plus 1/6 V2 equal to 3/2 volt. Okay, so add together, this becomes V1 plus 1/2 V2 equal to 3/2. This is my first equation. I will take KVL to loop number 2. Okay, so in this we will have loop number 2. So we'll have 1/2 V1 plus 1/3 V2 equal to 5/6 volt. So this is 1/2 V1 plus 1/3 V2 equal to 5/6. This is second equation. 2 equations, 2 unknowns. As I said, most of the time you cannot, but in some specific cases you can rely only in KVL, but in most of the cases you cannot. Now if you solve this, you will find that V2 equal to 1 volt and V1 is equal to 1 volt as well. Okay, nothing wrong here, everything is good. Now imagine that because of some measurement errors, because of something happened in the system, instead of measuring 5/6 volt, you instead of 5/6 volt, you measure 1 volt. So there's a little mistake. It's around 18% error happened in the measurement because of your measurement system. Okay. So what will happen here? If you try to solve the system, you will find that V2 equal to 3 volt and V1 is equal to 0 volt. See how much deviations happens here? For a small deviation in the input, you have a very large deviation in the output, and we call this in mathematical terms, L system. System is very sensitive to changes in the input, and this system we have to be very careful when we deal with it. We have the system of equation. We are expecting that if a little change in the input happened, a little change in the output will happen. And this is in most of the cases correct, unless your system is called an L system. We'll not go deep here, but I just want to show that some terminologies that you might have heard in linear algebra can be really correlated to circuit as well. This is what I just want to, I don't want to cover more than this for the traditional techniques. So with this, we are done with the first part of the notes here, which is dealing with linear equations, but we dealt with normal algorithms, non-iterative algorithms they called, which is Gauss elimination, and the modification to this to get rid of some of the problems that is we might face in Gauss elimination using our approach, which is partial fitting. So here there is a question. Let me address it. Can you please explain the small change was? Oh, never mind. Thank you. Okay. It's called L means sick. L system. It's an L system, not L means it's an L. It's a sick system. But we don't say sick, we use the word L. Okay. Now let's entertain you with the bonus question. Okay. So this will be your bonus question number 4. I already have a folder for that. So let me just go out from here. Let me introduce a page here. Or let me just write it here, the question, doesn't really matter. So let me write down here the system for you. This is your bonus question. I will give you like 5 minutes to solve it. I want to find x1 and x2. So this is the system, 0.001 x1. So this is 0 plus x2 equal to 3. So this is the first equation. The second one is x1 plus 2x2 equal to 5. Please use whatever you have learned so far in the course and try to find x1 and x2. I will give you like 3-4 minutes. Please go ahead. Let me insert a page so that I can solve the question. Okay, let me see how the submission is going on here. Okay, so we have only one submission. I will give you like a couple more minutes. I will solve it. I will solve the question. So make sure that you understand how to deal with this. And this summarizes almost everything that we covered so far. Okay, now much better. We have 4. Good. Okay, we have 11 now. Okay, I think that's enough. Hopefully there is one correct answer there. I will check after the class. So let's see how we will solve this question. Okay, first of all, I will try to solve this question. If I forgot about partial pivoting, I will see what will happen if I just handle the system as if I don't know about partial pivoting. 3 and 5. So, okay. So I will keep it as it is and see what I will get. So if I do this, so I need to subtract row 2 minus 1 over 0.001 row 1. Okay, and if I do that, this I will get 0.001, 1, and 3. I'll get here 0, 2, and 5. Okay, so sorry, this will not be 2. This will become minus 9, 9, 8. And this becomes not 5 minus 2, 9, 9, 5. So minus 9, 9, 8 x 2 equal to minus 2, 9, 9, 5. From this you can find that x2 is equal to 3. Okay, and if you substitute there 0.001 x1 plus x2 equal to 3, if this is a 3, then x1 is equal to 0. So this will be the answer. Now, if you go back here, okay, if substitute here is 0, x2 equal to 3. Let's satisfy this equation. If you come here and have x1 equal to 0, x2 is not 3, it's 2.5. So this is wrong. So you will notice that if you really, just a second, let me just divide these two numbers exactly how much you will get. 2, 9, okay, just a second. 2995 divided by 998, it's equal to 3, it's actually 3.00100 something. Okay, so if you use like 3 significant digits, then you will get 3.00 and you get here 0. Okay, now let's try to solve the same thing, but if I use partial pivoting, we'll see how things will go. Okay. Okay. So if you try to solve it with partial pivoting, then it's clearly that I need to reorder the equation. So this has to be first 1, 2, and 5, 0.001, 1, and 3. And if you solve now this system, you will find that x2 is equal to 3.02, 3 significant digits, and x1 is equal to minus 1.04. Even if you use 3.001, it still does not give you the right answer. And if you check, you will find that this is the correct answer. Okay, so partial pivoting is really very, very important that you have to pay attention when you solve your problems. The last thing I will today introduce to you iterative techniques. This is now completely new topic to you, and we will see what do we mean by iterative techniques, why we use it, why we don't stick to the Gauss eliminations with the partial pivoting, etc. So here, this is an iterative technique that we solve these linear equations. We have to start with an initial guess. We have to start that, okay, x1, x2, x3 is equal to this, okay? And then we solve for x1, x2, x3, and then we keep on repeating. And we use the absolute relative approximate error after each iteration and check. So let's say if I said do this until your error is less or equal than 0.001%. So you check for each variable until each one satisfies this condition, then you will stop the iterative process. Now, why we have to do this? First, it helps us to control the round of error, as elimination methods as Gauss elimination are prone to round of error, as we have seen. Also, if you understand the physics of the problem, and if you know that your values has to be around this number because of your understanding of the problem, then you can start your initial guess with something close by to these numbers, and then you will be able to solve this. More importantly as well, when you work with a very, very, very large systems, dealing with them using simple linear algebra, the system may not be able to solve. You will get an L system, you will get a very sparse system, you will get into too many troubles. So iterative techniques is the standard method we use to solve large systems. Now, for example, myself, I'm coming from an area of power system, although we talk about here nonlinear equations, but as we will see on, we will build our knowledge of using solving linear system to the non-linear equations, which we have to use this as well. Okay, so let's move on here. How to deal? How we can handle this? So again, here I have a set of linear equations. These are my variable x1, x2 until xn, and we have an n number of equations. So how to deal with this? I will express each equation with respect to only one variable, meaning I will make this equation x1 in one side and the rest in the other side. So here it will become equal to x1 equal to c1 minus a1 to x2 minus a1n xn divided by a11. I will come to this equation and I will make it in terms of x2 now, not x1. So x2 will equal to c2 minus a21 x1 minus until minus a2n xn divided by a22. And so on and so forth until I reach xn is equal to cn minus an1 x1 minus an2 x2, etc., divided by ann. So I made an n number of equations, each one x1, x2, x3 until I reach xn. Once I rearranged the equations, I will start with the initial guess. So you have to start with certain value. So let's say x1 is equal to 0, x2 is equal to 1, x3 is equal to 1, etc. Just an initial guess. And as I said, in reality, we have understanding where is my system and then how we'll deal with this. So this is how we write the equations. This is in summation format. Now we will learn about two methods. The first method, we call it the Jacobi method. This is how it started. And then Gauss-Seidel, they came and they modified a little bit Jacobi method to make the conversion much faster. So they are basically the same technique, the same approach, that you need to rearrange the equations so that you can rewrite them in terms of x1, x2 until xn. The only difference between the two, how they update their initial value or how they update their iterations, as we will see. So and then we will use the absolute relative error, which is what is the current answer, what is the previous answer. So you take the subtract both of them and divide by the current answer. So this is what we call the absolute relative approximate error, percentage wise, and you compare it to your criteria. Once all the variables reached to this criteria, then you stop your iteration. Let me see this examples. In this example here, we have the following. We have a 4 by 4 system, okay? And this 4 by 4 system or 4 by 4 equations, as you can see here, we have 10x1 minus 2x2 plus 2x3 equal to 6, okay? And then we have minus 10x1 plus 11x2 minus x3 plus 3x4 equal to 25, etc. Okay, so we want to solve this system using this is the initial guess that we will have. Everyone is equal to 0. So we need to start with rearranging the equation. So, okay, you will have that. Now let's go back to the first equation. It's 10x1. So I will keep 10x1 in one side and divide by 10 everything. So we'll have x1 is equal to the rest. Okay. So we will have here x1 is equal to 1 over 10. And then we will have the rest. What is the rest that we have here? We have x2 plus 2 minus 2x3 plus 6. So we have 6, and you will have plus x2 minus x3. So this is your x1, and there is nothing for x4. Now we will go for x2. Here, this is your x2. Now I will take everything to the other side and divide by 1 over 11. Okay, so this becomes equal to 1 over 11, and then I will have my 25, then plus x1 plus x2, thank you, 1 over 11, 25, x1 plus x2, and then minus 3, x3, this one. Here are the equations. I mean, I don't need to waste time. So here are the equations that we will have. Okay. So this is your x1. This is there's no, of course, there's no x2. This has to be x3. Okay. And then minus 3x4. Okay. And so on and so forth. Okay. We are done. We rewrite the equations. Now, I want to find x1 as a first iteration. My first iteration. Okay, so the initial guess that I have is that everything is equal to 0. So I will substitute this with 0, this with 0. So your x1 equal to 3 over 5, or it's equal to 0.6000. Let's say I want to keep 5 significant digits, so everything is like this. Now, and here pay attention. Now, x2, and here is the difference between the Jacobi method and the Gauss-Seidel. This is the only difference. I will come here and I want to substitute. I will see 1 over 11 x1. Now, what is the value of x1 I should use? Should I use x1, the initial guess, when x1 was equal to 0? Or the most updated value of x1, which is the 0.6. Jacobi says use the initial guess in all the steps until you finish, and then use the updated value. So you will use 0 here. Gauss-Seidel says no. Why I have to use the 0? I have a better estimation of x1 because I already solved for x1, so I will use this. And you can tell that this will make the iteration much faster. You will converge eventually, but the Gauss-Seidel will converge to the right answer faster. Then plus 1 over 11 x3. I don't have any value of x3 except 0, etc. So this is your x2 as your second iteration. This is equal to 2.272 7. Now we go for x3. In x3, I have x1, x2, and x4. Again, x1, I have two values, the 0 and the 0.6. x2, also I have two values, the 0 and the 2.2727. x4, I have only one value, which is the 0. Okay? And Jacobi method, which we are doing right now, I will use the 0, the initial guess, until I finish the first iteration for all variables. The Gauss Seidel, no, they will use the most updated value. Okay, and we keep doing this. So this is the x1, x2. So we can see that everything has been substituted by 0. Everything is by 0, and we'll get x1, x2, x3, and x4. Okay, so this is my initial guess. Now I will go for the second iteration. Of course, usually problems does require few or even more than few iteration until you reach to the right answer. So you keep doing this, and here is the answers after 3 iterations. So this is your initial guess. This is the initial guess that you have. Everything is 0. Then after the first iteration, you get 0.6000, 0.22727, etc. Second iteration, the values are start to change. Now, one of the factors that you have to watch if your answer is converging or diverging, how smaller is my error? Is my error getting bigger and bigger or smaller and smaller? You expect that the error start to get smaller and smaller. It will be a little bit of oscillations, but eventually it will start to, you will have a smaller and smaller error. After 3 iterations, these are the answers I have, and the correct answer, this is 1, 2, -1, and 1. Still, we are a little bit far away from the answer, so we need to do much more iterations. And this is the main drawback of the Jacobi method, that it converges, but it will take very much time to converge because of the large number of iterations you have to do. Next class on Thursday, we'll talk about how Gauss Seidel modified the method and how he managed to make it faster. And then we'll talk about some of the problems that we will see in iterative techniques. It's not 100% proof. There are some certain issues. We will see those issues in next class. How do we know on which iteration we should stop without knowing the correct final answer? Okay, as I said, you have to use the relative approximate error. So, for example, here, let's say that we decided that, or it's given to you that the error should be less than your error should be less than or equal to, let's say, 1%. Okay, so what do? We reach, for example, in the third iterations here. So you find the approximate relative absolute error for all of them. So you find the error of x1, which is equal to 0.9326 minus 1.047373 divided by 0.9326. Okay. Let me just calculate. This is just for the sake of the calculations. Okay, so this is equal to 0.9326 minus 1.0473 divided by 0.9326 times 100. So this is like around 12% error. Very, very high error. Still, we are very far from the right answer. You keep you calculate the error for every single one. And when you stop only when all the errors satisfy this criteria, then you will stop the iteration. This is how you stop when you're working with iterative techniques and you don't know the answer. This is why we said the most practical way of the error is the approximate error, because in most of the cases we don't know the final answer.